Digital remote sensing. Digital remote sensing has several advantages over the photographic remote sensing. Photographic imaging can be performed within the optical region, especially photographic region of the electromagnetic spectrum. Whereas digital remote sensing or digital imaging can be performed in the optical region, in the thermal region, as well as in the microwave region. Photographic image cannot be collected in high spectral resolutions, and therefore it is not possible to obtain hyperspectral images in the photographic remote sensing. Digital processing is also not possible on photographs. Digital processing means digital image processing is not possible on the photographs. Scanned photographs are sometimes used. The photographs can be converted into digital media, but we have to remember that most of the digital image processing techniques of, for example, image classification, image transformation, extraction of information from the images by means of computer algorithms or computer processing or digitally program, it is not possible. So, we must need digitally captured, digitally stored and digitally captured, digitally stored and digitally transferred data. Digital remote sensing can be performed from the satellite platform as well as aerial platform. Although satellite platforms are more preferred because a satellite platform has several advantages as we have discussed earlier. So, these are the primary advantages of digital image processing, and that is why digital image processing is and that is why digital imaging or digital remote sensing is becoming very popular, and the photographic imaging or photographic remote sensing is nowadays obsolete. In a most generalized way, a digital image is an array of numbers depicting spatial distribution of a certain field parameter. For example, reflectivity of electromagnetic radiation or emitted temperature or geophysical or topographic elevation, etc., etc. So, digital image contains digital image consists of discrete picture elements, and this discrete picture elements are called pixels. Pixels are basically the smallest two-dimensional non-divisible element of an image, and each pixel holds a number that is called the digital number or the DN value. DN value may be the reflectance value, it may be the emitted temperature, radiant temperature, or it may be the earth elevation or anything else. Now, for the digital imaging, we need sensors. Now, what is a sensor? Sensors are devices used to take observations. A sensor is a device comprising of optical components or systems and a detector or array of detectors in the focal plane with the electronic circuitry. Sensors are characterized by their spatial, spectral and radiometric resolutions or radiometric performance. They are available in a variety of forms and combinations nowadays. Additional types of sensors are expected to be developed in the near future. Passive sensors detect the reflected or emitted electromagnetic radiation from natural sources, while active sensors detect reflected responses from objects which are irradiated from artificially generated energy sources. For a simple example is, say for example, radar or microwave remote sensing. However, our discussions will be limited within the optical region only. We are not going to discuss the artificial sources of energy. Therefore, we are going to use the passive energy or passive source of energy. Now, there are sensors, some sensors which can create images. There are also some sensors which cannot create image. For example, thermometer is also a sensor, but it does not create an image. It is therefore a non-imaging sensor. It is a non-imaging sensor, but a digital camera, for example, in digital camera, as we have discussed, several instruments are there. However, in the digital camera, we have the charge coupled devices that is responsible to generate a pixel, and this CCD can produce image. So, we may have non-imaging sensors and we may also have imaging sensors. However, our discussions are limited within the imaging sensors. Now, sensors that instantaneously measure radiation coming from the entire scene at once are called framing system. These framing systems will capture the entire scene in a single instant. However, an entire scene can be captured with a longer duration of time, I mean with multiple instants. Then they are not framing systems. So, if the scene is sensed point by point along successive lines over a finite time, not in a single instant, this mode makes up a scanning system. So, imaging system may be a framing system, that means non-scanning, or it may be a scanning system, that is non-framing. Now, digital sensors mounted on the satellites are always of scanning types. However, sensors that we use in the aeroplanes may be of both types, scanning and non-scanning. But remember, non-scanning cameras or non-scanning sensors are rather more popular in case of aerial remote sensing or aerial platform. Now, what are the basic components in a sensor? In a sensor, we have several components. First, say for example, is the dispersing element. What is a dispersing element? Dispersing element basically disperses the light or splits the light based on their wavelengths. A very common dispersing element is prism. All of we know that prism can split the white light based on their wavelengths. But in the sensors we do not use the prism, rather a different instrument is used, that is called diffraction grating. This diffraction grating is a dispersing element. Other than this, we also have filters. Filters are used to subtract some unwanted energy and allow to pass a selective portion of the energy. Then we have spectrometer and spectroradiometer. These two devices, spectrometer and spectroradiometer, are principally similar, but the term spectroradiometer is used in the multispectral remote sensing, and the spectrometer, the term spectrometer, is preserved for the hyperspectral remote sensing. Other than this, we also have the detector, which detects the light or incoming energy. Now, let us try to understand the detector. Now, here we have the filter, for example, through which the light is coming, and there is the detector. In the detector, we need the power, and here we have sensing material. This sensing material becomes excited when the energy or when the light falls on it, and as a result of this excitement, it releases electrons, and then this electron goes out in a voltage waveform. And for example, if we can install a voltmeter kind of instrument over here, then we can measure the voltage, output voltage, and this amount of output voltage can be used to assign the value of a pixel. So, the pixel value will be determined by this voltage waveform or the amount of voltage. Now, if we have higher amount of incoming energy, then more excitement over here and more electrons are being released, then the amount of voltage is also higher, and as a result the pixel value is also higher. Now, on the earth surface, brighter areas reflect more energy, and as a result brighter areas will appear brighter on the imagery, since their pixel values will be rather higher. Now, for a darker area, it reflects lower amount of energy. As a result, the incoming energy towards the detector will be rather lower, and as a result lower excitements over here, and as a result lower amounts of electrons will be released, and the voltage will be rather lower, and the pixel value will be rather lower, and it will appear darker on the imagery. Now, an image is created with many pixels. So, an image is basically an array of pixels, many pixels will be there. Now, from the previous discussion, as we have seen that a detector creates a single pixel in an instant. Now, the question is how the entire image will be generated, because in the entire image we have many pixels. It is basically a two-dimensional array of pixels. So, there are different techniques for generating the image. A single detector can be used. Theoretically, it is possible. Practically also, it was implemented in the earlier remote sensing ages. One line of detectors can be used, and area array detectors can also be used. We shall discuss them one by one. First, image acquisition using a single detector. So, this is the detector, and this detector will create only one pixel in an instant. So, how the two-dimensional image will be generated? Now, the sensor will have a rotation, and because of this rotation, it will be able to focus on different ground areas, and in this direction the sensor will be rotated and one line will be completed. But by this time the flight will move forward and the scanning will start from this point again, and the next line will be captured, the next line will be captured, like this. Let us try to understand this concept with the animation. So, in a single instant the sensor is creating a single pixel, then in the next instant the next pixel, then the next instant the next pixel, and so on. So, once the one line completes, by this time the flight moves forward and then the scanning starts for the next line. So, thus it can create a two-dimensional image by using two different motions. One is the sensor motion and another is the flight motion. Okay. So, as you can see, it is basically time consuming, and since two different motions are being used, there are several problems associated with it. We shall discuss them later with greater detail, but before that, the next is image acquisition using detector strip or one line of detectors. So, here we have multiple detectors and actually we have one line of detectors. Therefore, sensor motion that was required in the previous case is not required in this case. So, here all of the sensors arranged in a linear array will capture or will generate one line of pixels. And definitely after capturing one line, the flight will move forward and then the next line will be captured. So, it is like this. The scanning is being performed line by line. Okay. So, one line is being captured in an instant. So, this is much faster, and definitely since it is faster, therefore, it can focus on a specific area for longer duration of time. As a result, the spatial resolution becomes better, and these two are basically, the previous one and this one, these two are basically scanning techniques, and these two are being used from the satellites, but the previous one is now almost obsolete, and in most of the cases currently we are using this second scanning technique. And as I told you that both of these techniques are basically scanning technique, and they are being used from the satellites and as well as from the aeroplanes, but from the aeroplanes this second option is most preferred, and from the satellite also nowadays this second option is being used. Then this third option, this is basically the framing system. It is not a scanning system because the whole scene will be captured in a single instant. So, here instead of a single detector or one line of detectors, here we use two-dimensional array of detectors, or they are called area array detectors. and this area array detectors will be used in the film plane, and instead of film, this area array detectors will capture the image in a single instant. The entire scene or the entire area will be imaged in a single instant, as you can see over here. Next, let us look at a greater detail in the imaging by scanning technique. And as we have discussed earlier, that if the scene is captured point by point along successive lines over a finite time, then it is called a scanning system, and a framing system basically captures the whole scene in a single instant. It does not require a longer time. But in case of scanning system, the capturing the entire scene takes a longer time. And scanning techniques can be operated from the aerial platform as well as the satellite platforms, as we have discussed earlier. And two modes of scanning are there. One is the across track scanning and another is the along track scanning. Across track scanning theoretically uses a single detector. As you can see, here we have the detector, okay, and here we have a rotating mirror, okay. Light comes from this ground cell and the entire light will fall on this mirror, and this mirror will reflect the energy towards the detector and it will be sensed, and in an instant only one pixel will be generated. And then what will happen? The mirror will rotate in this direction and it will focus on the next pixel, and the next pixel will be recorded. Then it will again rotate, the mirror will rotate again, and then the next pixel will be recorded, and thus one line will be scanned. By this time, the flight will move forward and the next line will be scanned, and this is the way by which we can generate the three-dimensional image. And this technique has several disadvantages. First of all, it is extremely slow, and second thing, since we are using mechanical instruments like motors, etc., therefore its precision is not properly maintained, and several wear and tear problems are there, and it may malfunction sometimes. Further, since it is extremely slow, therefore it cannot focus on a specific ground resolution or ground cell or area on the ground. Therefore the spatial resolution becomes coarser. Spatial resolution is not very good in such cases, but we have to understand that this is the older technology, and earlier in first commercial remote sensing satellite, Landsat MSS, this technique was implemented, and later in several satellite series as we have seen that they have used this technique. But this is the older technology, and nowadays across track scanning is almost obsolete, almost. And this technique is like this, as I have shown you. So we have a single detector and it is capturing the pixels one by one, and once it completes one line, scanning of one line, then by this time the flight moves forward and the next line is scanned, and then next line, and then next line, and so on. The scanning is being performed continuously, and in this case one strip like imagery will be obtained. It is similar to the strip camera. as we have discussed earlier in photographic remote sensing, the concept of strip camera was implemented in digital mode. Okay, so next is, before going to the next scanning technique, several remarkable series of satellites are there. For example, Landsat 1 to 7, Landsat 1, 2, 3, 4, 5, 6, 7, all are based on acrostack scanners. But now we have the Landsat 8 and Landsat 9. These two are using the push broom technique, or the technique I am going to discuss later. Then several other series are also there. Now, along track scanning. In case of along track scanning, we use linear array of detectors, one line of detectors. Okay, and the entire line on the ground will be scanned in a single instant, and by this time the flight will move forward in this direction, and then the next line will be captured, then the next line will be captured, and in this way one line of imagery, or one strip of imagery, will be captured. Now, this is again similar to the concept of the strip camera. Okay, one strip of imagery will be captured, but here instead of using a single lens, we are using one linear array of CCD. And here, as you can see, we do not have the mechanical instrument like motor. Therefore, the reliability of this sensor and the accuracy of this sensor is also better. Since it is faster, therefore it can look at the ground for a longer duration of time, because this entire line is being captured in a single instant. Therefore, it can focus on this on a specific pixel for a longer duration of time. As a result, the spatial resolution is always higher in comparison to the across track scanning. Now, this along track scanning is can be implemented in the satellite, can be implemented in the aerial platform as well. The basic concept of the along track scanning, as I have shown you earlier. So, this is one line of detectors, and one line of pixels will be generated in a single instant, and the flight will move forward, and it will capture the next line, the next line, and next line, and thus it will generate a strip like imagery. So, this is again a scanning technique. Now, see, we have discussed two different techniques of scanning. One is the across track scanning and another is the along track scanning. There are different names exist in the literature for these two scanning techniques. First, the across track scanning, the previous one, the first one. For the across track scanning, it has several names like optomechanical scanner, since optical and mechanical instruments are associated in it, or it is also known as whisk broom scanner. And this next one, this along track scanning, this is also known as push broom technique, or it is also known as optoelectrical or optoelectronic scanning, as because we are using electronic and optical instruments and we are not using any mechanical instrument. So, several names are there, basically they are same. We have only two different approaches for scanning. Now, other than the scanning, we before going to discuss the non-scanning technique, first let us see. The first along track scanning was French spot satellite. So, all spot satellites are using along track scanners. All Indian remote sensing satellites or IRS satellites are using along track scanners. And as we have discussed earlier, Landsat 8, Landsat 9 All satellites launched by private agencies or the European agencies, Sentinel satellites, all are based on push broom technique or the along track scanner. And in future, basically the along track scanning will be used and the across track scanning will become obsolete. Now, Indian remote sensing satellites. Indian remote sensing satellite. We have several remote sensing satellites either launched or will be launched, but all of them, all of the Indian remote sensing satellite optical sensors are based on push broom technique, all of the optical sensors. Now, what are the optical sensors are carried by Indian remote sensing satellites or IRS satellites? So, we have linear imaging self scanning sensor, LIS. LIS has 4 different generations: LIS 1, LIS 2, LIS 3 and LIS 4. Then we have panchromatic sensor to capture the data in a single band. LIS sensor is basically a multispectral sensor. It captures imagery in multiple bands. Then we have wide field sensor. It can capture imagery in 2 bands. Then we have advanced wide field sensor. It can capture imagery in 2 bands or in 4 bands. It can be programmed. Then we have ocean color monitor that can capture imagery in 8 narrow spectral bands for oceanographic applications. Then we have multispectral optoelectronic scanner. It can capture imagery in 3 and 19 spectral bands for oceanographic applications. So, these are the optical sensors that are used by the Indian remote sensing satellites. Now, let us discuss the hyperspectral imaging. Hyperspectral imaging or hyperspectral remote sensing is based on the push broom scanning technique or along track scanning technique. And in case of hyperspectral remote sensing, as we have discussed earlier, they can capture imagery in very narrow spectral bands, as narrow as 0.01 micrometer. And hyperspectral remote sensing is not possible to capture photographically. They must be captured on the digital media. And since in case of hyperspectral imaging, the bandwidth becomes very narrow, therefore the amount of light also becomes very less. And since the amount of light is very less, as a result, they are necessary to be captured from lower altitudes, not from higher altitudes. And as a result, mostly hyperspectral remote sensing images are being captured from aerial platforms rather than the satellite platforms. And in case of hyperspectral remote sensing, we use imaging spectrometer. As we have discussed earlier, that spectroradiometer is used for the multispectral remote sensing, and imaging spectrometer is used to capture hyperspectral imagery. Now, what is the basic concept of hyperspectral remote sensing? Now, in case of hyperspectral remote sensing, we have a lens, and see, this is based on the along track scanner or push broom technique. The flight is moving in this direction, for example, and we are capturing one line of imagery. Okay, one linear array CCD is used, and one linear array CCD is used for one band, to capture one band. If we need 2 bands, then we need 2 linear array CCDs. If we need 3 bands, then we need 3 linear array CCDs or 3 linear array detectors. So, that is why here this is one line that is capturing, say for example, one specific wavelength, another line is capturing another wavelength, another line is capturing another wavelength, and multiple images are being captured. So, although it is being shown as area array CCD, but it is not actually area array CCD, rather it is a linear array CCD, and multiple linear array CCDs are being used to capture multiple bands or multiple images. Now, the light from the ground will pass through the lens, and then this light will be focused through a very narrow slit, and then this narrow slit will allow the light to pass through another device that is called collimator, and this collimator is responsible to make the light in a very thin film. Now, this thin film of light will fall on a dispersing element, and this dispersing element will split the light based on their wavelengths, and then this light will pass through again a lens, and then it will again fall on the CCD, linear array CCD, and different linear array CCDs will generate different bands, and we will get hundreds of bands in hyperspectral remote sensing. So, finally, to summary, the hyperspectral remote sensing is based on along track scanning, where we are using linear array CCDs. Next is non-scanning technique. The non-scanning technique means basically it is a framing system, framing technique. We use digital frame camera to capture the imagery. These digital frame cameras are very similar to the aerial metric cameras that was using film for capturing the imagery. But instead of film at the film plane, now we are using area array CCD. That is the basic difference. Now, in case of digital metric camera, it uses an area array CCD, and the entire scene is captured in a single instant. And this is an example of digital metric camera, and here we are discussing the principle. As you can see, here the sun is illuminating the object. This is the Earth surface object, for example. So, the light will be reflected by the object, and after reflection it will pass through the imaging system, where we have the lens, diaphragm, etc., etc., and then the light will fall on the film plane, where we have area array CCD, and the area array CCD will generate the output image in a single instant. It is similar to this concept that we have discussed earlier. The entire scene will be captured in a single instant, and that is why it is not a scanning system, rather it is a framing system. Now, all these techniques are used for optical remote sensing, or for the light that is within the optical region of the electromagnetic spectrum, that is within 0.3 micrometer to 3.0 micrometer. Now, thereafter starts the thermal region 0.3 micrometer to 1 millimeter, and then we have the microwave region 1 millimeter to 1 meter, and in these two regions also remote sensing is possible. And this remote sensing, thermal remote sensing and microwave remote sensing, these remote sensing techniques must use the digital imaging technique. However, their techniques are rather different. They use different sets of instrumentations and interpretation of their imageries etc. are also different. That is why in our course we have limited our discussion to the optical remote sensing only. Thank you.